Yeah, welcome back. It's good to see you here. Just as I get started, while we are warming up, I was wondering if anyone had some logistics, just something that I saw a good bit of ed activity, so that's nice. And we've been working away on a chatbot, ChatGPT enabled class bot. So we'll hope to unveil it this weekend. And it's listening to all the ed discussions, so that's good. Any thoughts? I mean, any roadblocks as you get? I mean, a big thing I think I asked you is get a wallet, which is not a bad thing. I also asked you to form groups. Any trouble anywhere? Any stumbling blocks? Anything we can help? I'm going to take the test. All good, right? Excellent. And you do know that assignment one, programming assignment one, is due next week, Thursday next week. And did I tell you that ChatGPT does really well on it? Feel free to try it out. We're really trying to go after the principles of the software stack here, and actual syntax and figuring out Rust is, feel free to take AI self. No qualms. Okay, let's get started. Last lecture, we started with kind of a very modest goal. What are blockchains? This lecture, we're going to enable, just double click on this. Again, what are blockchains? Except this time is a lot more a computer sciencey way. Last time I took like 20,000 feet. I started with trust and human societies and how blockchains are a siren song that human societies have been listening to and organizing themselves with. Very high level stuff. And then this lecture will take a very low level, like on the ground. This time we look at it as a data structure. So it's like the other direction. They're right on the ground, maybe underground. Along the way, we'll learn a few basic cryptographic techniques, primitives you could call it, not even techniques, primitives that we'll use throughout this course. They're prevalent all along in blockchains. It will be used in your programming assignments. We'll use them in your homeworks as some abstractions with idealistic properties that we'll use. So they'll be used everywhere in this class. But it's on a need-to-know basis, and they're largely derived out of decades-old cryptography. And a good bit of assignment 1 and 2 are about just getting to feel for these libraries. So they're already built. It's not something you're reinventing, and just getting to use them as a library call function. Okay. At the end of this lecture, we'll look at a blockchain as a data structure. We're going to look at three primitives, three cryptographic primitives, really two. And the one is a hash function and a variant of hash functions, where if you have many hash functions, then you can accumulate them. So that's a hash accumulator called a Merkle tree. So really one hash function, and then a signature, a digital signature. And hash functions alone help you create what I would call sort of a blockchain as a data structure, but it has some centralization issues and properties. And signatures allow us to have multiple parties interact and have a decentralization bringing to this data structure. So I used these words last time: trust, a decentralization. And this time we are kind of nailing them down in a very quantitative and sharp way and representing them as data structures. And how these two, like high level and low level, interact is really much of this class, where we build a whole system around these data structures. Okay, so a hash function is a function, so it gets started. So it takes an input x and outputs y. And here's an example function. And it's just a 256-bit output modulo of any large number you give, right? You give an integer, x is an integer, y is an integer, and it's just modulo 256 bits. So 256-bit output. Y is always 256-bit output. First of all, it's a deterministic function. So for a given x, you always get the same y. There's nothing random about any of this. It's also simple. I mean, computationally simple. And the other thing is that it's This has a randomness feature. If you think X is random over a large enough size, then Y is likely to be random as well. So there is some inherent, what one may call, collision resistant aspects. You pick two X's at random, then it's not very likely. I mean, the likeliness of the corresponding Y's, the outputs of this hash function being similar, are equally spread out among all the possibilities. The larger the space of X, the better this collision resistance, but I'm just trying to point out that there's a natural inherent favor. Not trying to nail down a mathematical property, but I'm appealing to some intuitive thinking here. Okay, these are some functions. So hash function is defined via just a couple more additive properties. Just define this, where you have arbitrary size input. The input is not constrained to be of any fixed size, just like in the example before. X could be any integer. But the output is fixed size. In the previous example, it was 256 bits. It should be deterministic function, so there's nothing random. It should also be simple, simple as in computationally simple. You should be able to run it very efficiently. That's what I mean by, yeah, efficiently computable. And finally, you would like to minimize collisions. So that is, two X's chosen at random don't lead to the same Y. And that was sort of an example of a function. Hash functions are used routinely in databases and information retrieval, where if you have already a key value pair where the keys are already integers, then you can just itemize the values by that as a row number. Then you're looking up is easy. You can just say row number 4, go there and pick up the retrieval is easy. But what happens if you're retrieving, I don't know, images or data which is not naturally ordered by integers? Because ordering is so much easier if you have integers, they're fully ordered set. And hash functions are routinely used in such cases. You have something called hash tables, where you take your data that you are trying to, that's your value, take a hash of that. Now that's an integer, 256 bits in this previous example, and that gives you its key. So you can represent the data by just this particular key and go and retrieve it. So hash tables are a convenient way to represent and retrieve data. Collision resistance comes in handy. Now you see why collision resistance was useful, because two different data, if they give you the same key, then it's kind of a hassle. Then you have to worry about it. So if the data sizes are very large, chances are the keys are not the same. Okay. And they're just a basic building block of databases. But we are looking for hash functions, but cryptographic hash functions, which really has just two extra properties. First is collision resistance, but adversarial collision resistance. So previously, collision resistance, I was being a bit intuitive by saying two different inputs, X1 and X2, but kind of chosen randomly, unlikely to give the same output Y. But this time, I'm looking for adversarial resistance. That is, given data X, you should not be easy to find another data input X prime, which has the same, both of which have the same outputs. So this is a distinction from just regular hash functions. And this is what makes cryptographic hash functions a lot more involved and tricky to build. And it's a constant game. I'll allude to this. The second one is very related, but it's the converse. That is, it should be hard to invert. And the function is invariably on 2, because X is, input is unconstrained, output is always constrained. So clearly it's an onto function. So there, for every input, there exists some other input which has the same output, yes. But it should be hard to go back and find it. Computationally hard this time. Informationally, it's in principle, yes, but computationally hard to invert. So it's like a one-way function. Easy to go this way computationally, but hard to come back. So it's not hard at all. Both of these things are not are really, no, it's going to fail with the previous example I gave, that the modulo 256. Because it's very easy. Give me a 256 thing. It's very easy for me to find any number of inputs with that as the that output. And similarly, it's very easy to invert. I mean, it's there's no, yeah, you can have any number of inversions. So one-way function and adversarial collision resistance are very related to each other. Okay, we'll do this attack on, actually, I think we should do this in our homework. So let's leave it. Let's leave some surprises there. I said it's a primitive, a cryptographic hash function. I've only alluded to through its properties, like mythical properties. It's not even clear such things exist. They do. And it's been a constant upgrade in cryptography over the decades to come up with cryptographic hash functions and to find them broken a few decades later, and then the new generation comes along. I'll give a few of this. Maybe we'll try to do one homework around this. It's possible. I'm trying to be careful about, just a bit of logistics. At the end of each lecture, I'll try to give a bunch of reading exercises and homeworks or questions to try out. Only a subset of them will actually show up on your homework. So at the lecture notes, feel free to explore at the end of the lecture notes some of these pointers. And definitely we have given pointers to some of this history of building cryptographic hash functions and attacks on them. So the cryptographic hash function we will use throughout this class and is used in Bitcoin and largely in all altcoins, that is coins other than Bitcoin, is something called SHA-256. 256 refers to the output size. So the larger the output size, the more it's sort of secure. It's harder to break cryptographic hash function. It's 256 bits. And SHA-256 is the one that's state of the art. It's not been broken. Doesn't mean it won't be. There's no proof on this, but so far it's the cornerstone of all coins around. It'll also be the cryptographic hash function that you will use in this lecture, in these lectures, and in this course through your programming assignments. And as it's a library function that you can call, you'll get to play with it in your assignment, where the input is fixed, 768 bits. Output is always fixed for hash functions, 256. And you wonder, didn't I just say that the input should be arbitrary because I should be able to take any block and hash it down? Yes, but SHA-256 as a library only works with fixed size inputs. So the way, and it's a classical way that can convert such a crypto primitive, a primitive hash function into take arbitrary size inputs is through this so-called Merkle-Damgard transform. I mean, it's the most basic thing that you try. If you have a large size, what are you going to do? You can only take 768 bits. So what can you try? Yes? Yeah, but how do you, that's the rough idea. If it is smaller than 7, that's right. Oh, can I get your name? Tim. So Tim is saying that if it is smaller than 768, you just pad it with something, and that's good. What happens if it's larger? That's usually a problem. Yeah, you can cut into multiple things, take hashes, and then put them together, and then again cut, and then hash, and at the end eventually may have to pad something and get your function. Roughly, the Merkle-Damgard transform is the same thing. Also a primitive that you can use regularly in your assignments. How to prove that if you started with a cryptographic hash function, the overall, this Merkle-Damgard also gives you a cryptographic hash function that's why those names are there, to prove that was bulk of the work. And there are variants around it. Sort of, again, we'll give a bunch of reading material in your lecture notes, kind of outside the scope of these lectures. It's a fun activity on its own. A class on cryptography would cover this at length. It's considered secure, and largely what we will do is that in your assignments, we'll just use this. In your homework assignments and in the conceptual development of this class, remember the two principles. There's the conceptual principles and the engineering design principles. In engineering design principles, we'll just use this as a library function. And in conceptual principles, we'll just do what is this called a random oracle model. That means it's an ideal hash function. An ideal hash function gives you this property that the output is random for any given input x. And no matter how tiny the change in the input, I just change 1 bit, then the output is completely random again. I'm going to make this assumption. And it's a theoretical assumption that will be helpful when we do any conceptual thinking, let's say security analysis. This is so-called ideal hash function model. Nothing in practice has shown that this is not appropriate. So it's a good approximation. Okay. we are done. This is what we'll use, except we just need one last property, and we'll not really use it in this lecture. We'll use it very much in the next lecture, is that I said it should be a one-way function. That is, it should be hard to invert, but I want it to be also allow me to specify some part of the input. Let's say the input gets broken into two parts, and the second part is already given. In this case, it's referred to as this is the second part. This is the first part. And I would like to find the first part given not the hash value, but less than something. So in other words, I should be able to solve puzzles like this. Notice that this is equation, right? This is a 256-bit number. This is also a number, let's say 256-bit. Then you want to know, and this is already given. You would like to find this first part, which satisfies this equation. And I would like my hash function to be amenable to such calculations. And at the same time be hard, computationally hard. That means finding this part should be hard, because that would is tantamount to inverting something. Of course, the hardness will depend on the threshold. If the threshold is the entire, all 1, 1, 1, 1 ones, then pretty much anything will work, right? If it's just all ones, 256 ones, then that's the largest value possible. Then anything will be less than that. So that's in some sense the easiest. So in other words, you should be able to solve hardness, and the hardness is controlled by this threshold. And we'll get into more of this why, but SHA-256 is quite amenable to solving such puzzles. And it's hard in this kind of an inversion method. So that means just giving part of the input doesn't make it any easier to find the other part while satisfying an equation like this. Yes, Aditya.
Obvious why adversarial collision resistance already does not imply this.
It's a good question. So Aditya is asking, isn't adversarial collision resistance already giving this? It's possible. And I don't know an example of a hash function that does not satisfy this, but satisfies the other one. But that could be just maybe. I just put this down as something that we do want. And it's possible that every cryptographic hash function gives this. I haven't thought through this fully. It's not clear that all of them do, but it's, yeah, not clear. Thank you for that. That's right. It's not the sharpest statement. I don't have a counterexample where you really need this as an example, as an extra property. And such functions are the ones that we will use. And especially what I already used the word puzzle generation. And in fact, I mean, if you may be new to blockchains, but you've all heard of something called mining and Bitcoin mining. It's a thing, actually. A lot of people know about this. It's just in the popular mind. And mining refers to solving equations like this. Solving means finding nonce. And yeah, that's actually the mining process. We won't get there yet. You have to hold on till next Tuesday for that, where it fits into blockchains. But that's actually what mining refers to. Now that I already had a hash function and I described this requirement, I might as well say what mining is. Mining is basically solving this equation. Well, it's not a unique solution because there could be many nonces, but you just have to find one. And it's a variable difficulty process because the larger the threshold, the easier this solution becomes. Yes. Constantine? That's the point, that you have different block hashes, then and maybe different thresholds makes it each time a new puzzle. Especially different block hash. I mean, this will change. If you keep the same one, of course, then everything is the same. And I don't even know what block hash really means. Just think of it as some data that's been provided. We'll see by the end of this lecture what those things are, but not yet. This is clear? So this is the first primitive. Yes, question.
How is mining wide sort of that security? Once the problem is solved, does it not matter?
Hold on to that thought, okay? I haven't still given enough context. Can I get your name? Ori. That's right. You such, yeah. So Ori is asking the question is that once you find that, like, where does this come in into blockchains? I mean, I think even just broader question. He has something much more specific, but we haven't really given enough context. I just wanted to be able to say how hash functions could be potentially useful. And I just wrote this down and I mentioned it. I haven't given enough details to really answer that question, but not far. Just by next week, we'll already be there. Next Tuesday, we'll already be there. Okay, so that's what hash functions and particularly cryptographic hash functions are. And I promise that we'll define blockchain as a data structure and and hash pointers. So let's, before we even go to cryptographic hash pointers, we can just look at hash pointers. And I said it's great for information retrieval. That's a very standard use of hash functions, hash tables. But hashes can also be used to create a linked list, where you can have a series of data that are linked to each other. And the link in a normal linked list, you point to the memory location where the data is. Here, it's not the memory location, that doesn't really is immaterial, but it's the hash of the previous data. So hash of an information, in some sense, is a pointer to that information. It's unique to it, given collision resistance. And you can think of it as a proxy for that information. So if you ever want to order any data, then you can simply have your data and a pointer to the previous one. And a pointer is now the hash of the previous one. That's it. It's not a memory pointer. It's a hash pointer. And this is a way to sort of retrieve the information, but with another thing. In a memory thing, you just go to the physical memory location in a memory pointer. Here, because it's a hash pointer, when you go retrieve that information, you can also check that information has not been tampered with, because I have the hash. If that information got tampered, the hash of that presumably changed too. See, we're already getting to use this collision resistance right away. And so this is a way to build a linked list, which is tamper evident. So regular pointers can be used to build linked lists and other data structures, binary trees. So we'll get to binary trees here too. But hash pointers can now be able to build a linked list where you have tamper evidence of any tampering. Let's look a little bit deeper. So in fact, this is already a definition of blockchain. Blockchain is a hash pointer based data structure, and it's a linked list. So let me just explain this, and then we'll explain why it's like a blockchain. So what is a block? Block has two parts. There's a data, which is what it should have, and it has a header. The header is a pointer to the previous block. And this pointer is simply hash of the previous block, as we just discussed. It's a hash pointer. And the point of this is that I have and I start with one place, let's say the Genesis block, and I keep building my blocks by just pointing to the previous one. Notice that the information of the very first block, called the Genesis block, this is a thing in blockchain. The first block is always called a Genesis block. That is embedded in the very last, what I'm calling the head of this chain. How? Because the hash of the Genesis block is in the second block, right, as the header. And that itself is a whole block whose hash is in the third block, in the header of the third block. And the block itself, or third block itself, gets hashed as the header onto the fourth block. So basically, all these blocks are encoded in the header of the head of this whole chain. And you change anywhere along this chain, then the headers of all the blocks change, including the header of the final block, the head of the chain. So having access to just the header of the head of this block is enough to control or be able to make any evidence on tampering of any of the blocks all the way before. And this is the power of this hash pointers and having a linked list through these hash pointers. And this is what it means to chain the blocks. So the chaining refers to tamper evidence properties of hash pointers. So once you've then this is called chaining, and so this is said to be a blockchain or simply a blockchain. As that's the phrase, and it's no longer a phrase; it's just a word. The blockchain. Does it make sense? This is a crucial point where we've defined blockchain now as a linked list data structure where the pointers in the linked list are hash pointers. And the property or the chaining alluded to in blockchain refers to tamper evidence by having the header of any one block, tamper evidence of all blocks behind it, any or all of the blocks behind it. Yes. Can I get your name? Ju. So Ju is asking a good question. Let me repeat it. He's asking, in principle, collision can happen. What are you going to do about this? How are you going to address this? There is no method around it. So if you break a hash function or a collision happened accidentally, it's all too bad. It's kind of over. So entire security depends upon collision not being broken or hash functions not being broken, them being unique. We'll do some calculations of what's the probability of that, assuming a random oracle model. So you can feel, can sleep better at night, especially if you're having coins in your wallet. But we'll do some calculations. That's why homework we have some homework, just so that you can do some paper pencil stuff, just so you can sleep well. But there's no other backdoor, nothing. Good, thanks for asking that. Yes, Ori.
If you wanted to verify that a chain was untouched, would you not have to calculate all the hashes from the beginning?
That's right. That's right. So now I think Ori is alluding to a question, which is he's saying, suppose I want to check, but very specific entries. I'm going to just generalize your question, okay? Then do I have to go and ask for the data for everywhere along the way and check all the hash functions and then go to the head? In other words, if all I wanted was, I wanted to make sure that a specific entry in a specific block is there. Do I have to get all the data from everybody, calculate the hashes, and make sure the hash of the final block that I have, the head of the block matches? Well, that'll do it. But isn't it an overkill for something simple that I wanted? And this is exactly where we'll get to in the second part. That's what hash accumulators are for. So remember, I said there were two parts in the hashes that I needed to see, hashes and hash accumulators. We'll get there. And that's precisely this topic. If I'm interested, so this is a blockchain, right? You have data in all of these blocks. Block 0 is also called the genesis block. And then you have blocks afterwards. So every block has a number because it's a chain. And right, block 1, block 2, block 3, so forth. In Bitcoin, there's a block every 10 minutes. It's been going on for about 15 years. So we can check that number. That's what the blockchain looks like. The pointer is simply the hash, and you just form this list. In practice, in your implementation, you'll also have memory pointers because that way you can actually build the list itself. But that's not necessarily conceptual. In the lectures, I'm not going to go into that, but in your assignment, you need to actually also have a pointer, and that's kind of being alluded to here. So having the hash of block 3 is enough for me to check any tampering happened anywhere else, because at any point I can ask for the blocks, and I can do the hashes through a percolated way. And if any fault change should have changed the hash, and this is using the property of hash resistance, the collision resistance. Toledo? No. Tadios.
So I'm kind of confused about what the data you're storing is in this like.
Excellent question. So first we'll answer Ori's question, and then we'll get to Tadios, which is, what is this data? Like, why at this point I've just chained together data, and I'm trying to make sure it's not it's not being tampered with. But what is it? So all these are great questions. In fact, we'll all answer them all in this lecture. We'll make it pretty clear what are canonical examples. In principle, then just the power of blockchains is that it doesn't really matter. It could be just an ordered set of instructions that can be compiled by a computer that understands what it is. But we'll try to look at it from a cryptocurrency perspective right now.
Part of the question is like, why would you want to check and go to a blog? Like, are these all like different? Are they coming from different sources?
Let me give, so Tedious is asking a question, where does this tamper evidence come from? So here's an idea that's been around from the 80s, actually. And that's when the hash functions were first invented. And this is called digests. So suppose I have a document and it's like a patent, or it said that I already had this information. And how do you prove to someone else a few years later that you already had it? Or you have kept the data without any change. It's like a vault, like a storage vault. And this was actually a thing. People would take the hash of this data and publish it in a newspaper. So that presumably that is always available. It's like a broadcast of the hash. At any time, someone can check with me whether I still have the data and not tampered with, both of these, by simply asking what my data is. And by downloading the data and taking the hash of that and checking with the digest that was published in a newspaper like a decade ago, lets you confirm that this has not, it guarantees you ownership, that I actually had the data. And B, it tells you that it's not been tampered. So that's a primary usage, original usage. And it was actually a thing to publish hashes in newspapers. So it's like proof of having the data. And by retrieving it at any point, one can also check that it's not been tampered with. It's like a vault, data vault. It's a bit conceptual at this point. What does this lead to applications is, yeah, I agree, Tedious. We'll get there. We'll already want to do one example of a cryptocurrency, in particular Bitcoin. We'll already get started this lecture. And we'll see what data is in that particular application. It's a canonical application. You know, it's the first blockchain, and it's largely an important application. So can't miss it. But we'll first get to what Ori was alluding to, which is, how about searching for a specific data element as opposed to asking to download everything? So let's set this up. So I'm interested in block 1, and I'm looking at a specific data element there because maybe that's where, and I'll allude to it right away. And this is related to answering the question on what the data is, which is, suppose that's where my transaction is. You know, that's where the Bitcoin that I own has been, that I am the owner, was published there. And I just want to make sure it's there and nothing ever got overwritten. So that's just an example. And that's exactly one of the main key examples for searching for a specific data element. Yeah, so right now you have to have some way in which I can get this whole block, I can get the second block following and the block following. Well, I have the head of the chain, the hash pointer of the head of the chain, and I can check. Well, that's a way, but if people are just checking for a specific element, maybe you don't want to download the entire block, and also all the following blocks too, by the way. Otherwise, how else will I do? You want to avoid this. And this is done through a queue data structure. It's a binary tree of hash functions. It's called a Merkle tree, based on Ralph Merkle, who sort of invented this. And the idea is that you retain only the root of this tree, and allows you to do tamper evidence checks in a very efficient way on any of the leaves of this tree. So the data is actually the leaves of the tree. So let's get started. And it allows you to do proof of membership. That means, is a particular leaf this value or not? And it does it in an efficient way. You can also do non-membership, but let's do membership first. So this is how it looks like. Here's your data, and let's say I chopped it up into smaller chunks, and these would be the leaves of this tree. How am I going to build this tree? Well, I take a hash function, so that's the symbol, and I create the next level above. So these are all hashes of these blocks. So this was my data block. right? Big data block. I chumped it up and took hashes. So those will be now the leaves of this tree. The hashes are the leaves. You put every pair, every two of these hashes, you group together, hash them. And you create the next layer of this tree. Each layer has half the number of blocks because you're just taking two at a time and putting them together. Here I started with 8, I went to 4, now I'm down to 2, and I combine them and hash them together. I just have only one hash. And that's the root of this tree. And this root of this tree is what anyone keeps as a proof or as a digest of the data block. And this is related to how we did previously. Previously, you would have just done a hash of this whole thing, this whole block as one group through perhaps a Merkle-Damgard transform, and that would have been its digest. This time, I just went through this somewhat a little bit more elaborate process, not by a whole lot, but similar, related process, by which I divided up the blocks, I took their hashes and combined the hashes, and then combined yet again and yet again until I got to just one root. This is called a Merkle tree, or it's a way of accumulating hashes. If you have a bunch of hashes, you accumulate them. And this is a hash, it's called so-called hash accumulator. Okay, so what good is this? It's specifically designed that having the root of this tree allows you to efficiently check for membership on a given block. Let's say I want to check this particular block. And I should be able to only download this block. Well, but how do I check? And I can ask for block number 5, and perhaps the owner of this data will give you this block number 5. That's good. At least it's better than downloading the whole data. But how am I going to, just knowing block number 5 is not, and I only have the digest, right, which is the root. How am I going to check? I can check this hash, but I don't have it. I only have the root. So what else do I need to get to the root? So the data owner, actually, maybe I should pause and get what people would like to say. Go ahead, Niyusha. Yeah. Yeah, so you heard Niyusha. So let me give anyone have something to say on this? Tino? Oh, what's the question? So the question is that I want to check this block, okay? Well, one way to check the block is, and I asked for this block, because my transaction is buried there. I have something specific about that particular sub-block. And I ask for it. And then they'll give me, because whoever has the data is claimed to have the data, they'll give it to me. But how do I check it? How do I know that it was not tampered with? I only have the digest up there, notice. Normally, if I had a whole block as a baseline, if I had a whole data block and I had its digest, its hash, then I could ask to be given the whole data and I can calculate the hash myself. And then I know everything was correct as it should be. But this time, I'm only interested in this sub-block. Okay, I'm not interested in the whole data. Whole data may be much larger than what I'm interested in, way larger. So I'm not interested in downloading the whole block. And I want to be efficient, which is what Ori was alluding to. And but I want to be able to check though. I can't trust. That's the whole point of having this hashes. That was the question. Does this make sense? And what I was alluding to is that if I had this hash, that I could have checked. Evan? No. When?
Would you need 3 more hashes? Like hashes up to the root to figure it out?
Yeah, so when is good. So, right, I think Niyusha said this in the same way. So take a look at this. This hash, I don't need. I have it. Because I've been given the data, I can do the hash myself. But if I were given that purple hash, then I can use that to construct this red one. And if I were given that one, its neighboring hash, purple are the ones that I'm asking to be requested, then I can go and construct that block hash myself. So I don't need it. And if I were given its sibling at that level, then I can go construct the digest and I can check, because notice that I already had the digest, so I can check. So if I want to just verify subblock number 5, the owner of the data block, of course, has to give subblock 5 because that's what I'm requesting. Along with it, it just gives 3 more hashes, as Ben pointed out, which is the purple ones. Notice that the red ones I can compute myself. I don't need to be given. I'll do that. No, thanks. I can do the calculation myself. And the one at the top, the pink one, is something I can check now with what I already had. This is a proof of membership of a data as small as you want, along with a few hashes. How many? Well, the height of the tree. Yes.
I know you still only need to give them like log and
That's right.
is it n still like a really big number?
Can I get your name?
I'm Ben.
Ben. Okay. So Ben is asking, let me repeat Ben's question. He's saying it's log n. So that's good. You only need log n hashes, where n is the number of, let's say n was 8 here, right? So Ben is asking, is there a way to cut even that log n? You know, I don't know, log n, or make it constant. And if n is really, really large, isn't this a hassle? Someone wants to say something about this? Notice that the units are a bit off. The log n refers to hashes, which are always 256 bits. But the data size itself is in arbitrary dimensions. I mean, this could be very, very large, but the hashes are always 256. So you brought it down substantially. The units are off when you counted the data. Whereas the data could be very big, but hashes are fixed size. Yes?
Does that mean
That's what you should do. That's the idea. That's the, whoa. Okay, I didn't do anything. When?
Setting the largest possible Merkle tree will be log of 256. Like it doesn't like
I suppose that should, yeah, that's like, yeah, because you don't want to make this too small, because at some point you start suffering. 768, I think that's the, yeah, roughly, yeah. 40?
Yeah, if you're only, if you compared the root hash that you calculate what's actually there, say it's wrong, what information does that really give?
It tells you that something got tampered with.
But it doesn't tell you which block.
Presumably you are interested in which block, because I'll get there. So we're getting a little bit ahead, but yes, it doesn't tell you which block. This doesn't help you look for trouble. I mean, it's help for people who already have a specific thing in mind they want to check. They're not interested in the whole universe. But if you want to check, find that needle in the haystack which may have been tampered with, you need to have everything. That's true. And we'll get to this in later in, I mean, you're asking a question which is, let me put this 2 ways. So you want efficiency where someone is, you want to be efficient in a what we call optimistic path, where let's say nothing is happening, but I just want to check what I care about. Merkle trees are good for that. What you are looking for is what I may call the pessimistic path, where you need to really check, man. I mean, I don't know. I can't just check individual things. I need to be sure. Then you need to do everything. There is no shortcut here. Yes. Can I get your name? Abhi.
But does that mean that if you do all the calculations and you digest it, does that actually tell you that your block is tampered?
It's not your block. The block that you requested has been tampered. That's what it says. And perhaps that's enough for you to.
So that's under the assumption that all the other given those blocks are.
Notice that they could not have calculated those blue box. This is where the hash resistance property is. It's not, okay. I think Abhi is getting to he's basically hitting the nail right on its head, which is there a way for the block owner to change this block and still hide this change by giving the purple blocks appropriately? This is actually the exactly hitting the nail on the head. And the answer to that is, it's not easy. If you change that, it's not easy to find that purple block that once you change that block, notice that the red block changes right up there. And now you have to find that purple so that it matches the next upper one. and the next upper one, and so forth. So it's not easy to invert hashes. So this where it's critically used. That's actually, thanks for that. This is the key point, is that it's tamper evident, but also it's not easy for an adversary who has the block to pretend otherwise. Okay, questions. Thaddeus?
So like, I don't have access to membership. Where do you get?
Okay, these are great questions. Please hold on upon that. I think you asked this earlier too. Basically, you want the whole user experience, right? The entire system around it. Right now, I'm just giving a data structure and giving you want to see the whole elephant, and I'm only showing you bits and pieces. Completely agree. I just ask for a little bit of patience. We'll get there. Actually, end of this lecture, we'll already have a pretty good idea of all of what you're alluding to. And another lecture, you'll be in good shape. But there were some questions. Can I get your name? Henry?
So my question is, like, where do you store all the hashes, like this binary tree of hashes? Do you store it in a distributed manner? And that means if I want to check, I need to ask, like, people maybe at the end, I know the Earth, and it may take a very long time for me to even check, even a very small thing.
So Henry is asking the question, which is more or less what Thaddeus was asking, which is, what's the system around this? Who are the participants? Who is checking? Who is keeping this? Why does anybody care? All of these questions, I agree that we haven't even alluded to, and I can easily see that it's top of mind. But again, just a bit of patience, and I'm just not talking patience beyond this lecture. We'll already get to build a system around it where someone keeps the data and there are some others who check. And this is the beginning of a cryptocurrency setup at the very early stages, at the very beginning. And we'll get there. Just a bit more patient. There was another question. Similar. Can I get your name? Kristen. Thank you. Just a bit. Hold on for this, okay? And that's the proof of membership. So, but I just want to say one thing though, even though I'm asking for patience. Suppose that one person maintains this data. At this point, let's say some kind of a trusted party. But you trust but verify thing, I mean, I kind of trust you to hold it, but I'm going to verify every now and then. Is that be okay? So then you're not worried about where it's stored. One place is being stored on Dropbox. Let's just make it clear. AWS. It's stored on the cloud, but you want to verify, I don't know who else has write access to it. I have read access. I don't have any write access. Okay, let me answer this and we'll take a short break. I think I always find it good to take a short break in a class lecture like this of this length. Suppose there's a centralized storage sitting on Dropbox, sitting on AWS, on Box account, and a lot of people have read access, but every now and then they want to verify that it didn't change, and a lot of people have been given the digest, the root of the Merkle tree. But they want to check every now and then but it contains all emails or all the data of everybody in this class, and I want to check my part. And the Dropbox owner will provide your data, obviously, that's your block, sub-block, along with some purple hashes, so that you can verify that the digest we published long ago has not changed. So at least your data has not been tampered with. In fact, your data has definitely not been tampered with. Does it make sense, Henry? That's our application already, where the data is just stored in a centralized place where many people have read access. Question, yes. That's right. So turns out, can I get your name? Owen, that's right. You mentioned last time, Owen. So Owen's question is that, yes, you'll know its tamper has happened, but you don't really know exactly where it happened. Turns out tampering is just a bad thing. Knowing tampering happened is already a five fire alarm. It's like a major alarm. So finding down exactly where else has happened is not, at that point, basically, hell's broken loose. And at that point, you don't trust anything and you don't trust this node. So a lot of other things will kick in. So exactly finding the nitty-gritties of where else the tampering happened is less relevant at that point. At that point, I don't trust anything, this kind of a feeling. We'll get there, but that's an application-specific thing. We'll get there as well. So I just want to conclude this and we'll take this break. So that's what a blockchain with a Merkle tree representation is. Previously, I said a blockchain is simply a chain of blocks where the chaining is through hash pointers. Now, and that's the header, right? The header is the hash pointer. But now the header not only has the hash of the previous block, which is dash, because that's the pointer, and that's the chaining, but it also has the Merkle root of the data in the previous block. So this time, you not only are the blocks chained together, you can't unchain them because the hashes are there, but you also can't go and change the data in any of the blocks because the Merkle roots or the hashes, specifically accumulated hashes, are embedded in the further blocks and hence propagated throughout the block structure. So head of this chain of blocks is enough to find evidence of tamper in a quickly searchable manner, in any specific entry that somebody might want to check. And I'll stop here. This is, we'll take a break. I don't mean to leave. So, and in a way, this is an example of, so I think this is what a full structure would look like. And to answer Henry's question, to really set it up, such a blockchain provides a centralized structure where the centralization refers to someone who holds and maintains this database. But the trust is only to be able to have the data there and be available and be responsive to questions. Can't just shut down and say, oops, sorry, not available. So that's the only sense in which it's trusted. If it's ever data gets rewritten, I'll know it. So it's tamper evident in a lot of any number of read access people, but it's centralized to the extent that only someone is holding this data. And Henry was alluding to the fact that perhaps this data should not be kept at one person or one place. And that should get decentralized as well. And still everyone should be able to access it. And this is the second part of this lecture. And we'll use digital signatures to do identity management of different parties. So signatures allow you to have an identity. And once you have an identity that is not spoofable, then you can have a claim to having some actions. And we'll build a blockchain where one person does not need to have this full ownership of storing it. And at that point, we already have all the elements of a cryptocurrency. And one more lecture, lecture 3, we're pretty much ready to see all of Bitcoin. Okay, if you're okay with it, let's take just a couple of minutes break. Just to, Shall we restart? Yeah, so I think this part is going to be a relatively, let's restart. And our goal this time, right, what we've done so far is to have this blockchain data structure to create, if someone could hold the data in one place and allow us to query, then I should be able, and then I have ability to store a data there and check that no one tampered with it and in some efficient way. So that's what we've done so far. And the good news about the chaining is that the data can be added sequentially. Because that's the point of a linked list, is that if you just had one data, right, static, and you had its whole digest, then how are you going to ever update the data? Like add things or having a new block. So good news here is that it's not simply a storage, it can also be added, and things can grow sequentially because the blocks can keep on coming and the linked list can keep growing. So that's good about blockchain. It's all set, but it's centralized in the sense that someone stores it. And that's the only trust you need to do, just to be able to have what we call data availability. The data should be available. And yeah, it can't be, they're not going to tamper with it. And data can get added along the way. New data comes, I can just chain it, put a new block and keep chaining it. All that's good. And notice that this chain is also ordered. That means there is nothing, not only data inside the block got tampered, but the ordering of the blocks also cannot get tampered with. Okay. That's already at a basic level an element of a cryptocurrency. But let's just to do cryptocurrency, we need two things. First, Thaddeus was asking, or someone who asked, who asked, like, what is the data? I think Tino was asking, like, what is this data? And in a cryptocurrency, they're simply coins and transactions involving coins. And so that's sort of the answer roughly. And we'll take a closer look at what a coin is. But most of all, we need to have an identity for different parties who can maintain the data, and identity for the coins themselves. And both of these things are done in one shot through digital signatures. So you can generate a signature. A signature is a pair of keys, a public key and a secret key. And just as what you may think based on their names, public key is your identity outside. Secret key is what you keep to yourself. And you can generate it. And you can use these keys to do two things. First, you can sign. If you are the owner of this identity, then given any message or a data block, I can sign it. Signatures are always done through secret keys. And the output is the signature. And the second part is that anyone else can verify. Given the message and the signature, an outside party can verify using the public key that this signature is kosher. And that's the identity management. You always sign with your secret key. You can't sign with your public key. You always verify with your public key. And you don't need the secret key to verify. Of course, if you have the secret key, it's easy to verify because I can generate the signature myself. But that's not the point. The point of digital signatures is that you should be able to verify using a public key while it was written only with secret key. And the entire point is that it should be unforgeable. Signatures should be hard. That you should not be able to generate a verifiable signature without knowing the secret key and knowing only, of course, everyone knows the public key, but knowing the public key is not enough for you to infer what the secret key may have been so that one can forge it. It's going to be a primitive. How these signatures are done itself is it's a very fascinating intellectual story. Just like hash functions, kind of like magic. I alluded to that in last lecture already. We'll take that at face value in these lectures. And in your class programming assignments, you'll think of them as libraries that you'll call. In particular, we'll use this library or family of ECDCA algorithms. And we will, in the theoretical analysis, we'll just assume that they cannot be forged. That means signatures have, a signature by one identity retains to that identity. It cannot be forged. And in particular, just like SHA-256 was 256-bit input, 768-bit output, input and 256-bit output, here the public keys are 512 bits, secret keys are 256 bits, and you always sign a message of a fixed size. But of course, in practice, you can sign a whole block by signing its hash. So you don't sign the whole block, you sign the hash of that, and hash is representing the block. So that's in practice. And the signature itself is 512 bits, just to give you an idea of what the signature looks like. Just sort of tens of bits, hundreds of bits. Make sense? And we'll use this in your assignment. This is used in Bitcoin, it's used in all altcoins. Okay, so now we are set to talk about how to do identity management. First, public keys are your identity. That's what everybody knows you as. In Bitcoin terminology, it's called an address. It's kind of weird, but it's called an address. It's 512 bits is your address, and that's how you are represented. That's your identity. It's also the identity of coins. We'll get there. Notice that there's no one's preventing you from having multiple identities. It's not like identity as a proof of personhood or any such thing. You can have any number of identities. An identity is simply a public key, secret key pair, and it's free to generate. There's no shortage of that. You publish the public key that's known for everybody else, and you keep your secret key, and your signatures are through secret keys. It's created, there's like no barrier to create by yourself, any number of them, and verifiable by everybody else. So this is how you get identity through signatures. And it's completely decentralized because I can completely do, but I don't need someone else to give my, like PUID, right? You need a university to give you an ID, you have a net ID, and it's verified by the university. So this one is completely decentralized. You create your identity, anybody else can verify your identity. If you do an action, signatures, they can verify you. And only you can sign. It's truly decentralized identity management. Yes, Constantine. That's right. So you're counting on the fact that these signatures are unforgeable and two people don't get the same identity. I mean, the space is so large. We should do some of these. I allude to them already. By the way, I think I just want to confirm this. We have lecture notes for every lecture. So I take a look. I mean, it's slides, of course, are available. The videos are available. We also have a summary of each lecture, like a one-pager. That's a real quick TLDR. But the lecture notes should have all of this, where we do some calculations on this and reading. But yeah, I just wanted to double click on that. Okay, now we are ready to get to Tino's question, which is identity management for individuals, like who could sign, but coins, which are the data in a cryptocurrency, are also identity managed through digital signatures. And the data is simply transactions involving coins. And the most basic transaction is creating a coin. You conjure up a coin, just mint it. It is called minting. And that's the most basic one. And you can consume coins and transfer coins and merge coins together. Like two different coins become one bigger coin with the larger value of the currency. And each coin, so a create coin refers to being created by a user, identified by its public key. And the coin has a recipient also identified by its public key. So pay coins is transferring coins. So let's take a look. So cryptocurrencies now look like managing coins, except the data involves transacting these coins. So let's take a look. The transaction looks like this. Pay this refers to a coin. You're just doing a hash pointer to that coin. And notice that coin itself has a public key, an identity. And Alice could be a recipient who's also referred to through Alice's public key. So this here refers to a coin, and Alice is the public key of Alice. Who gets to sign this transaction? That's what the blue block is. Whoever is the owner of a coin. So every coin gets to have an owner, and that started off with whoever created. The creator of the coin is the original owner of the coin. And anytime transactions are done by people who own coins and give it to someone else. This is the most basic part. This is this transaction. Create coin and transfer coins are the two key components of coin management in a cryptocurrency. It's a limited functionality of all the things you can do, right? I said the data could be arbitrary and there could be instruction set of a computer that you could compile and have complicated functionalities. But here I'm not doing any of that. I'm thinking of the data simply as either a coin being created or a coin being transferred ownership from one to another. So this is now the basic aspect of a decentralized blockchain then, where specifically a cryptocurrency. A block is now a header, that's the pointer, plus the Merkle root of the previous block, data of the previous block, and the data of this block, all stored as a Merkle tree, and this time key, signature. So someone gets to sign this block. Previously, I said there was a central authority, Dropbox, that was holding the data. But this time, someone gets to sign this block as having the creator or the, in Bitcoin terminology, the miner of this block. They get to sign this block. The header is the same. It's a pointer to the previous block, hash pointer. A pointer is the hash of the previous block header and Merkle root of the data of the previous block. Data refers to just the information specific to this block, which are all the transactions that we just discussed. The key thing which is new here compared to just a centralized version is that somebody gets to sign. And this, who gets to sign? Well, that's actually a question. I wrote down a list of questions already. Suppose this list of people who can sign is already there in an order. There were a few number of participants that want to agree. Maybe they go round robin through each one. Blocks have numbers after all. And we just take turns. Maybe we found a way in which we have ordered ourselves. We all take turns. And I create a block and I sign it. So people know that I did this. And everybody stores all these blocks. So this is the beginning, rudimentary start of a decentralized blockchain, where there is a fixed set of participants, and I'm calling them permissioned in this slide. That's why it's in red. Permission refers to the fact that it's a fixed number. We all know each other. We have somehow been permissioned, somehow decentralized, but still sort of power shared equally among us. But it's not permissionless, where anybody can come and anyone can participate in any amount. That's the ultimate version. The permission here is that, so I guess we can ask some questions. This time, let me ask the questions. I usually let you ask questions, but this time I think some people have asked you questions. And these questions are actually mirrored in some of the questions that I was seeing in Henry and Tadios and so forth, which is, how is this list of signatures, the order in which they should do, known ahead of time? Who are these guys who came together to form this cabal? And how did they agree already on this list? Which user in this list gets to add which block? Maybe some people should only be observatories and some people get signatories. And I mean, you have these issues in real life too. Corporations get formed, there is a board of governors, there are shareholders. I mean, these things are all real world issues, and they're done in, this is an entire area. I mean, corporate governance and corporate structures. And this is the early stages of that. Who is policing all of this, by the way? What happens if someone just doesn't follow this, goes out of order? What's the, I mean, where's the incentives and who is policing any of this? What we'll see in the next lecture is the answers to these questions, which allows anyone to be able to join, having no list ahead of time, and yet policing to be inbuilt in how, and answering questions 2 and 3 kind of get answered together. And this is the so-called Nakamoto protocol, or the longest chain protocol, aka the protocol underlying Bitcoin. And Nakamoto is the pseudonym who sort of invented Bitcoin. So it's also called the Nakamoto protocol, which is, I set up the questions and we'll answer them in the words of Nakamoto next lecture. Questions? I asked the questions this time, but yes.
So by Lecture2, you'll have the definition of the question.
Pretty nearly, except there may still be questions, which is why I have lecture 4, which is the entire Bitcoin system together. So what we'll do is that that's right, as Ben is pointing out, at the end of lecture 3, we'll have a answer, by the way. It's not the answer, it's a answer. It's Nakamoto's solution. And we'll take lecture 4 to just put everything together. And that also gives me an opportunity to go a little bit deeper into what your programming assignments are and what the software engineering principles are. And so far, you notice that I didn't design any engineering principles. I'm talking about like how to organize this, what's the fast way to efficiently do it. I mean, we'll do that in lecture 4. Lecture 5 and 6 will say, how good is this? We may have some intuition already in lecture 3, but we'll nail it down.